All right. So hello again to the second video from building AI chip, but like starting from the very first step by of course, building a calculator as a first step using Systemverilog, and then once you can create a calculator, then you can modify the code, make it more sophisticated, and then perform multiplication, and then you can um, like configure it or customize it for some AI applications, right? All right, so let me come again to the interesting video I studied from last time about understanding what is a module, what is a port, what is the instantiation. Let's go for it.
Imagine you've been hired as an FPGA designer to build a prototype ASIC calculator model. Before any logic is written, what is the very first step you take? So in this video, we'll begin by looking at the way we structure a system Verilog design using models, parameters, and ports. We are also going to configure model instantiation for our calculator model and outline the different subsystems that make up the ASIC-inspired calculator architecture. Then finally, we will explore how models are instantiated and connected to form a model instantiation for our calculator model and outline the different subsystems that make up the ASIC-inspired calculator architecture.
So the interesting, so it's basically explore rule outline as an inspired calculator, subsystem is and restriction for function. All right, so yeah, he basically used calculation as a use case. Of course, nobody would build a calculator using ASICs. It's very expensive, but it is a use case.
Systems that make up the ASIC-inspired calculator architecture. Then finally, we will explore how models are instantiated and connected to form a complete FPGA design. By the end of this video, you will be able to describe the structure of a system Verilog model, including the parameters, the ports, and instantiations. You will also be able to identify the key ports and parameters used in our calculator prototype modular design. And finally, explain the purpose of modular design and how submodels connect within a top-level model. To achieve these outcomes, we first need to align on a fundamental mindset shift when working with system Verilog. When designing FPGAs, it's crucial to remember one key point. We are developing hardware, not writing software. So this means we are not defining a high-level software architecture. Instead, we are describing the behavior of the hardware components and how they connect. So for our calculator project, we are going to break the design into several submodels. So this is a key principle in system Verilog and in hardware design in general. So instead of building a single monolithic block, we divide the design into smaller manageable units and assemble them into a top-level model. So now let's take a closer look at the specific components we are going to be building in this course. For our calculator model, we are going to split the design into the following key components. One, the earlier submodel, which performs the arithmetic and logic operations. Then we have the FIFO or register model. FIFO stands for first in, first out. So this will be used to store the result of calculations that we may want to reuse later. So it's our memory bank. And then finally, the top model, where all these submodels are connected and integrated into a complete system. So by structuring our design this way, the entire calculator becomes more organized, scalable, and realistic to how professional ASIC and FPGA systems are built. So now let's begin by looking at the way we structure our system Verilog design using the model keyword for our calculator model. We start with the model name. Our main model is named calculator. So next,
So yeah, it is interesting in how like the previous session was me expecting what would be the modules that is needed, the blocks, right? And now it is like the reference in what is really the correct way of thinking as a professional hardware designer. So the blocks that are here are mostly so we have here the allo um, for the calculation itself. You add two number, you subtract two numbers. So the calculation itself is performed here, and then of course you need to save it until you calculate. So you get the first number from the user, and then you get the second number. So after you get the first number, you wanted to read it. So this is all by FIFO. So FIFO, you read data and then you write it. So you keep it, and then you can show it. So this is also, of course, very essential. And then the top module, which will connect all everything together. And that is, of course, very interesting. Um, let me let me now show
Bo and
like the
realistic.
top level now.
So how professional ASIC and FPGA systems are built. So now let's begin by looking at the way we structure our system Verilog design using the model keyword for our calculator model. We start with the model name. Our main model is named calculator.
So from the higher level is like the main model name, and then the code will be encapsulated inside it. All right. So we have here the system Verilog.
So next,
The module basic will be the main one called, yeah, calculator, like main function, right? And um, it has 16 different parameters. hmm So the syntax looks a little bit different. Um,
are parameters. In system Verilog models, parameters act as local constants that let us customize a model's behavior. So when we instantiate the model elsewhere in our design, we can assign new parameter variables. So this means we can reuse the same model multiple times, each with its own configurations. Now that we have design,
mhm. Instantiation,
we
right?
can assign new parameter variables. So this means we can reuse the same model multiple times, each with its own configurations. Now that we have understood the overall model structure, let's focus specifically on ports, the inputs and outputs that allow models to communicate with each other. So in System Verilog, ports define a model's inputs and outputs. So you can think of ports just like the pins on a physical electronic components. So the port name must be unique, and the direction tells us whether the port is an input, an output, or an input for bidirectional signals. So in our example, for the calculator model, the operand, for example, is an input port of type logic and has a 4-bit data width from bit 3 down to bit 0. Then the start signal is an output port of type logic with a single data width of 1 bit. So also, data 1 is an input of data type logic with a data width of 16, starting from bit 15 down to bit 0. So this is because our width parameter is set to 16. So let us now walk through all the ports in our 16.
I find here interesting that the syntax here, they use the word which more or less as a const. So parameter which equals to 16. So 16 minus 5 down to 0, right? So this is like the size of or the width of the signal used for input and for the output.
starting from bit 15 down to bit 0. So this is because our width parameter is set to 16. So let us now walk through all the ports in our calculator top level model. So for our model, the first one is clock, is the system's heartbeat. On each tick, data moves, operation begins, and results are produced. We have the reset, which returns the design to a clean state by cleaning the FIFO. We have the push and pop signal. The push tells the FIFO to store the next incoming value, while the pop requests a stored value from the FIFO for LU reuse. Then we have the start, which triggers the LU to begin computation. The operand selects the operation the LU wants to perform. Then the data 1 and data 2. So the first data 1 is loaded into the FIFO for reuse, while data 2 is fed directly into the LU. And then finally, the data out, which outputs the final computed results. Let's examine the ports for our FIFO submodel, which handles the data storage. So typically, it has the clock and the resets, works exactly like it does in our top level model. The clock keeps the FIFO internal queues in sync with the rest of the system, while the reset will clear any stored value, allowing us to start from a no state or zero state. Then, when the push FIFO is asserted, we are asking the FIFO to accept and store a new value, adding it to the bulk of the queue. Then when we assert the pop FIFO, we are telling the FIFO to provide the next value that has been waiting the longest. So effectively removing it from the front of the queue. Then we have the FIFO in, which carries the actual data value that gets written into the FIFO when a push occurs. And then we have the FIFO full and the FIFO empty signal. So the full is a safety signal that lets the rest of the system know that the FIFO has reached capacity and it cannot accept any more data. While we have the FIFO empty, which indicates that the FIFO queue has run out of stored values, so there's nothing available to pop out from the FIFO. And then finally, we have the FIFO out, which is the data value the FIFO returns when a pop operation is performed. So making it available for the next stage of processing.
So this is I really like in hardware like the reusability. So of course when you design your model in a correct way, you can reuse it. You can reuse it better. For example, here they like yeah they are building a buffer like a FIFO. So of course like clock and reset are two signals that is gonna be used. But again, the logic will repeat itself, whether it is FIFO or LIFO or whatever buffer they are trying to build. Um, it will have these basic signals. So you wanted to push something, you wanted to pop it, and you wanted to write a data to be pushed, or the data that is read outside from it in order to give a signal when the FIFO is full, or a signal when the FIFO is empty.
So finally, let's look at the LU, the heart of our calculator, where all computation happens. So for the LU port, we have the start signal, which is what tells the LU to begin a new operation. So once it starts is asserted, the ALU captures its inputs and gets to work. Operand defines which computation the ALU performs, such as addition, subtraction, or another supported operation, so that the same hardware can handle multiple functions. Then we have the A and the B inputs. So A is the first input value fed into the ALU. So typically coming from the FIFO or a stored register. Then B is the second input value, often provided directly from the current input path. The result port holds the output of the computation, once the LEO has completed its work. Now, finally, we have the dawn signal, which acts as a handshake signal. So when dawn goes high, it signals the rest of the system that the calculation is complete and the result is valid for use. So together, these signals define how data flow through the FIFO and into the LEO, and how each calculation is coordinated from start to the finish. So, by understanding what each pod does in terms of system behavior, it becomes more easier to determine how they fuse up at the top level model. So, now let's do a quick recap of the key learnings from this video. So here is what we've learned. A system Verilog model follow a clear, consistent structure that defines how hardware blocks are built and connected. Breaking designs into earlier FIFO and top-level models improves scalability, readability, and long-term maintainability. Ports and parameters are essential for creating reusable, flexible hardware components across designs. So now I have a question for you.
So the question is, in a system Verilog design, you are building a CPU depth data path where the allo, register file, and control logic must be reused across multiple projects. Which of a module best fits this scenario? To automatically optimize the CPU for maximum clock frequency without the design input, no. To encapsulate the allo logic so it can be instantiated multiple times in different connection. Yes, or to temporarily hold intermediate value during the simulation only, no, to eliminate the need of to define input and output port between data paths, no, to encapsulate. I think, and this is the correct answer. All right, so that was interesting. Now let's head to the data and numeric types.
Now imagine you've already split your design into clean submodels and describe all the necessary inputs and output ports, just like we did. Now imagine you've already split your design into clean submodels and defined all the necessary inputs and output ports, just like we did before. So the next question becomes, how do you actually represent the data flowing through the models? And more importantly, what kind of variables and data should you use to model real hardware behaviors in System Verilog? So in this video, we're going to explore how literal values are represented in System Verilog using the binary, X, octa, and decimal formats. We'll break down the most common System Verilog data types, including the binary numerical vector types and how they map to real hardware. Then we'll also examine the difference between wire, reg, logic, bits, and other numeric types, and understand when each one should be used. And finally, we'll see the practical implementation of declarations and assignments on our calculator model and how these data types appear inside the real RTL code. So by the end of this video, you'll be able to describe how Systemverilog represents literal value. Most common Systemverilog data types, including the binary numerical vector types and how they map to real hardware. Then we'll also examine the difference between wire, reg, logic, bits, and other numeric types, and understand when each one should be used. And finally, we'll see the practical implementation of declarations and assignments on our calculator model and how these data types appear inside the real RTL code. So by the end of this video, you'll be able to describe our Systemverilog. So in this video, we're going to explore how literal values are represented in Systemverilog using the binary, X, octa, and decimal formats. We'll break down the most common Systemverilog data types, including the binary numerical vector types and how they map to real hardware. Then we'll also examine the difference between wire, reg, logic, bits, and other numeric types, and understand when each one should be used. And finally, we'll see the practical implementation of declarations and assignments on our calculator model and how these data types appear inside real RTL code. So by the end of this video, you'll be able to describe how Systemverilog represents literal values and explain the purpose of bit widths and base identifiers. You'll also be able to differentiate between two-state, four-state data types and identify when to use each in synthesizable versus tense bench code. Then finally, you also declare variables using proper syntax and choose appropriate types for synthesizable versus test bench code. So in this video, we'll explore the most common data types used in Systemverilog. This example represents the general syntax for defining literal values in Systemverilog. So the number before the quote indicates using and identify when to use each in synthesizable versus tense bench code. Then finally, you also declare variables using proper syntax and choose appropriate types for synthesizable versus test bench code. So in this video, we'll explore the most common data types used in Systemverilog. This example represents the general syntax for defining literal values in Systemverilog. So the number before the quote indicates the bit width in our example. They have a bit width of 3 and 4, and the character after it, the B, H, O, or D, tells Systemverilog which number system we are using. So now that we've understood how to represent literal values, let's look at the full range of data types available in Systemverilog. So in Systemverilog, different data types are chosen based on how a signal behaves and how it's used in design. So types like wire and logic are used to connect models and move signals around, much like physical wires in hardware. So with logic serving as a modern flexible replacement for both wire and reg. So for storing values over time in sequential logic, designers traditionally use reg, but today logic is preferred for cleaner and more consistent code. So when only two states are needed, you can use bit and int. Provide efficient two-state representation. And when integer types such as bytes, short ints, and long ints offer different bits and int, provide efficient two-state representation. And when integer types such as bytes, short ints, and long ints offer different bit widths for counters and arithmetic operations. Floating point types like real and short real are mainly used in simulation and verification to model real-world maths. And the time type is used to track simulation time and also to measure delays. So with this overview in mind, let's dig deeper model real-world maths. And the time type is used to track simulation time and also to measure delays. So with this overview in mind, let's dig deeper into how these types are organized into families. So system Verilog data types, they fall into two broad families. We have the binary data type, and then we also have the numeric data type. So the binary data type is used to model logic signals, wires, buses, and hardware parts, while numeric numerical data types are used to model whole numbers and real numbers. Let's start with signals, wires, buses, and hardware parts. While numerical data types are used to model whole numbers and real numbers. Let's start with numerical data types, which are essential for modeling, calculations, and counters. So they fall into two main groups, the whole number groups and the floating types. So for the whole number types, they include integer, ints, bytes, short ints, and long ints. While the floating point type include real and short real. Now let's turn to the binary data types, which is the foundation of all hardware signal modeling. So system Verilog logic and logic vector type. While a wire type cannot store a value and must be driven with a continuous assessment, a wedge can store a value. But system Verilog introduces the logic type, so which is a unified type that can replace both wire and wedge. So it works in a procedural block, it works in continuous assessment, and it's easier to use and far less confusing. So the only time you cannot use logic is when a signal has multiple drivers. So in that case, you must use a wire. So often we need multi-bit buses such as addresses or data paths. So we create those using logic vectors. In the example above, we have aerial logic internal signals. So they are internal because they are not external inputs or output ports. OP group. So this bit tells the LEO which category of operation we are performing. So like arithmetic versus logic operation. If we set it to 1, then we are performing an arithmetic operation, or 0 to perform a logical operation. Then we have the opcode. So these 3 bits pick the exact operation inside the group. So such as whether it's a add, subtract, and or. So next, let's examine the pick the exact operation inside the group. So such as whether it's a add, subtract, and or. So next, let's examine the internal signal function inside the group. So such as whether it's a add, subtract, and or. So next, let's examine the internal signal that manages our FIFO storage queue. So we have register 0 down to register 7. So these 8 registers act as our small storage queue. Each one holds a value waiting to be processed. So we use them to store results. Then we have register A and register B. So the register A is the read pointer. It tells the our FIFO which register to output its value next. And register B is the write pointer, which points to the register where the next incoming value will be stored. And finally, our full and NC signals. So the full is a simple flag that tells the FIFO that it has no room left to store data. And then the NC is another flag that lets us know the FIFO has nothing else to read out. Finally, let's see how these signals collect at the top level model. So for the top model internal signals, we have FIFO out. So this is the value coming out of our FIFO and heading into the area. We have the FIFO full and the FIFO NC, which is the status signals from the FIFO, so the top models know when it can push or pop safely. Then we have the LU result, which is the result produced by the LU after a calculation. And finally, our LU done signal, a signal from the LU that tells us the operation is finished. So together, this internal calculation, and finally our LU done signal, a signal from the LU that tells us the operation is finished. So together, these internal signals show how data and control flow through the system, from storage into the pipeline to processing by the LU, and finally coordination at the top level model. So by understanding these internal connections, we can clearly see how each block works independently while still contributing to the overall behavior of the design. So now let's do a quick recap of the key learning block works independently while still contributing to the overall behavior of the design. So now let's do a quick recap of the key learning from this video. So here's what we've learned. System Verilog represents literal values using bit widths and base identifiers B, H, O, D to specify binary, hexadecimal, octal, and decimal formats. Data types fall into two broad families: binary types for modeling logic signals and wires, and numerical types for modeling whole numbers and real numbers. The logic type serves as a modern unified replacement for both wire and reg, working in both procedural blocks and continuous assignments. Two-state types, bit int, provide efficient representation when only 0 and 1 are needed, while four-state types support x and z values for simulation. Logic vectors like logic 15:0 create multi-bit buses for addresses, data paths, and internal signals that connect modules in real hardware designs. Now, I have a question for you. Currently, you are building the memory subsystem for your FPGA model. You know you need to store multiple values, but how do you organize the data? So System Verilog gives you powerful array features to store groups of signals. But the real question is, how do you declare them, initialize them, and loop through them correctly? So in this video, we'll explore how System Verilog handles static arrays, including how they are declared and how many elements they contain. Then we'll learn different ways to assign values to our arrays, from individual assignments to array literal. and repeated value shortcuts. And then finally, we'll practice using for and for each loops to iterate through array elements and clean synthesizable out here. So by the end of this video, you'll be able to describe the difference between static and dynamic arrays in System Verilog, declare static arrays using both the System Verilog and the Verilog indexing style, assign values to arrays using elements assignments, array literals, repeated values, and defaults. So let's begin by installing Portus, which will be our primary software for simulation testing. So here I'm going to show you how to download Portus ID here we're going to be using for this project. You go to www.altera.com, click on Products, Development Softwares and Tools, Portus Prime Design Software. Then when you come here, you click on Downloads, and you can either go for the standard or the light edition. So when I click on the standard edition, I scroll down, I select the installer recommended, then I download the installer. So I accept the terms, then my download is ready. So double click on the installer. So we're gonna get this window. By default, these two devices are selected, Cycle and Max, and then we select our West Auto FPGA Start Edition and the Quartus Prime, which is our ID. And then down here, we agree to the license and agreement. And you can decide if you want to keep space to either select delete downloaded files after installation. The size is typically 40 gig after installation. Then down here, this is the size of the file we're going to be downloading, 4.65 gig. After installation, it's going to take about 40 gig of space. Then this is the download size here. So it's our size 14. This space required, and then available disk space. Down here, you set the installation path if you're on Windows. Over here is this very sensitive installation path. So this is the minimum checkboxes you will need because we need a test device for our project. Or if you're working directly with FPGA boards, you can select the exact boards you are using for your project. So when you're done, you click on download and install. So it's going to take a while for the download and installation to complete. So it takes roughly around an hour to download and install. So once it's done, you can just quickly open our software. So I'll see you when the download is complete. So when you first open for Portus, the fresh installation, you get this page. So you either want Portus in evaluation or you set up your license. So let's run it in evaluation. You click on it. So when you come to the home page, these are like recent projects I've run with it, or I'll first set up a new project. So I'll say click on the new project wizard and we give it a name. So we call it calculator. So I already have calculator one. Then you set up the working directory where you want your project to be installed. So in this first example, we are looking at how to declare static arrays in System Verilog.